Alright, so let's talk about mass spectrometry. So basically, infrared spectroscopy involves gives information about functional group right in a molecule, but it tells little about the size or what heteroatoms are present in the molecule. So for us to determine the structure of a molecule properly, we need to determine the molecular weight and the molecular formula. So basically, mass spectrometry is different from other spectroscopic techniques, even from the name. This one is spectrometry, but others are spectroscopic techniques. So unlike the UV, IR, and even proton NMR, um, so that involves the use of light, absorption of light. Basically, mass spec does not involve. So mass spec involves the bombardment of a sample molecule with high energy electrons. So in mass spec, a sample is struck by high energy electrons, causing the molecules to be broken apart in fragments. So the masses of the fragments are then taken as taken on the mass spectrum chart. So it's like you shooting a box with a gun and then weighing all its pieces. So let's say we have a given box. Let's say this is a box. I'm just using as an example. So let's say you shoot this box with a gun, right? So what happens is that the moment the bullet hits the gun here, so there is an ionization first, right? So first of all, there is ionization. We have ionization. Thereafter, there is fragmentation of the box. So this box is broken into fragments, right? So we have different fragments. We have small fragments. We have big fragments as well. So that's just the explanation there. So it's like you shooting a box with a gun and then weighing all its pieces. So let's see the next thing. Okay, so basically mass spectrometry ionizes a molecule in a high vacuum by bombarding it with a high energy electron, right? So you then sort the ions produced according to masses and then record their abundance. So basically, once ionization has taken place, we have fragmentation here. So thereafter, we sort these masses, we sort these fragments according to their masses, and then we display them on the mass spectrum. So the more massive fragment will be seen at the latter part, and the less massive will be seen at the earlier part here. So this is like the masses, right, of the fragments. So ionization is the first thing that occurs, right? So the neutral molecule M is bombarded with high energy electron. So this causes ion to be produced by knocking off an electron from the neutral molecule. So let's say we bombard molecule M with high energy electron. So the next thing we have is that we're going to have this high energy electron is going to knock off an electron from M. So we have two electrons thereafter, right? And this one becomes positive and radical. So when the molecule loses an electron, it becomes a positive charge, but also an unpaired electron. So I'm going to explain this. So the ion with both a radical and a cation like this is called a radical cation, or simply molecular ion, right? So let's explain this with the ionization of methane molecule. So this is methane. Methane is CH4, right? So we have this H4. We have this to be CH4, right? So all these can be written as a bond instead, we can write them as bond instead. Bond, right? So when you bombard methane molecule with high energy electron, so the first thing that happens is that this high energy electron knocks off an electron. It can be from here, it can be from here, it can be from here, or any point. So it knocks off an electron here. So this electron is knocked off. So therefore we have 2e negative, right? Plus we are left with this. So in most cases we still write the structure as this, right? We still write the structure as this, right? But we indicate at the top that it's now positive dot, showing that one electron has been knocked off. So this is a radical cation, or this is a molecular ion, right? So that's the ionization of methane molecule. So let's see the next thing. So radical cation is different from carbocation. So most carbocation have 3 bonded carbon atoms with 6 pair of electrons. So here is a carbocation. So carbocation, and this box here, there is empty electrons here. So most carbocations have 3 bonded carbon atoms with 6 pair of electrons in its valence shell. So but a molecular ion or a radical cation is basically this. So it has 7 electrons and 1 electron has been knocked off. So it's important to note that radical cation is also called molecular ion. So this is molecular ion, right? This is molecular ion. So it has the same mass as the parent or neutral molecule. So it's important to note here that from the illustration of the gun shooting a box, right? So this is a box. Let's say the mass of the box is 60 gram. Let's say it's 60 gram per mole, right? 60 gram per mole. So this is the molar mass of this box. So ionization of it does not change its mass here. So the ionization here, so let's put plus dot here. The ionization here that we have here does not change the mass of the box. So this is the molecular ion. So basically molecular ion always have the same mass as the sample mass, as the parent substance, right? It is when we fragment it that the mass changes. So this one could be like 10, this one could be like 5 gram per mole, can be this one could be like 2 and all of that. So also here we ionize this methane molecule, right? So basically ionization of the methane molecule does not affect its mass here until fragmentation occurs. So if this was 14 gram per mole, or we simply put mz equals to 14, right? So also this one will be 14, that is the mz will be 14, right? So basically it is important to note that yeah, we've said this, right? So it is important to note that radical cation is called molecular ion. It has the same molecular mass as the parent or neutral molecule. So the next thing is fragmentation. So aside the fact that bombarding a molecule with high energy electron leads to the production of molecular ion, right? So the molecule can also be broken down into fragments. We've said that if we have a box, you shoot it with a gun, the first thing that happens is ionization, right? So we have this same mass, right, becomes radical cation. So the first thing here is ionization. So therefore, after ionization, the next thing we have is fragmentation. So it could be of different sizes, right? It could be of different sizes. So this is fragmentation. So let's say the bombardment of ethane molecules with high energy electrons. So ethane is this, right? So we have hydrogen, 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 and hydrogen, right? All these are bonded. So when we bombard ethane molecule with high energy electron, what we have is first radical cation, right? So we have this first. We have this first, positive dot, right? So next thing that happens is fragmentation, right? So the fragmentation can actually occur here by just losing of one hydrogen, and it can also occur by losing of the CH3 group. So the first one, let's say this is A, let's say this is B, right? So the first one could be like we have C, hydrogen, 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 C, hydrogen, hydrogen. So this becoming positive plus hydrogen radical, right? So this like the first. We can also have this whereby we have C, hydrogen, 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 and one becomes the positive radical, and the next one becomes this, right? This. So this is like the these are different fragments that can occur. So basically fragmentation can occur at any point. So after fragmentation and after ionization and fragmentation have occurred, so different mixtures of ions are produced. Different mixtures of ions produced are separated according to their masses, and then they are detected on the mass spectrum. So now let's look at the mass spectrum actually. So let's talk about the mass spectrum. So the mass spectrum of 2,4-dimethylpentane. So dimethylpentane is this 2, 3, 4, 5, and we have hydrogen, 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 hydrogen here. We have hydrogen here. We have hydrogen here. We have hydrogen here, here, and here, right? So the mass spectrum of is 2-methyl pentane CH3, so 2,4-methylpentane. So this is a spectrum for 2,4-dimethylpentane. So note that the base peak does not necessarily correspond to the molecular ion peak. Alright, so basically looking at this structure here, when we ionize it, the first thing that we have on ionization is the production of molecular ion peak, right? So we have the molecular ion peak. So the molecular ion peak has the same mass as this parent compound, right? So if you calculate this one should give you 15, this one should give you 13, 15, should give you 14, give you 13, 15, 15. So everything should give you an MZ of 100 gram, right? So that is what we have here. The molecular ion has the same mass as the parent structure here. So 100 grams. So that's what we have here. So on so how do we have this fragment? So we have different peaks here, right? So the one at 85 is simply 100 minus 85. So that gives us 15, right? So 15 is equals to CH3. So basically this structure here the molecular ion peak, that is this, right, minus 15. That's what we have here. That is molecular ion minus 15, right? So that's what we have here. Or you simply put it as M plus minus CH3, right? So for this one is the same thing as 100 minus 57. So 100 minus 57 should give us 43, right? So basically that should be CH3, CH2, let's see, CH3, CH2. So this is 15, this is 14, that's 29. So we need what more? We need we need 14 more. 14 will give us, so that's like CH2. So if we have CH2, then we have plus 14, that's 43. So this should give us this 57, right? So let's look at it. When we fragment this, so let's look at the structure. So basically this compound here, let's write it out in a better way. So let's write it here. So this is structure once again, CH3, CH, and we have CH3, right? We have CH2, CH, and we have CH3, and we have CH3. So this is 1, 2, 3, 4, 5. So this is the 2,4 dimeter pentane. So fragmentation can occur here, right? So if fragmentation occurs here, what will be left? What we're going to have CH3 dot and CH, CH3, CH2, CH, CH3, and CH3, right? So this is like A. So this is going to be positive. So fragmentation can also occur here, right? So we're going to have CH3, CH, right? CH3, and plus CH2, CH3, and CH3. So, but looking at this, either of them can have the positive, and either of them can have the negative. But it's important to note that okay, let's say this one can be positive and this one radical, right? Or we can also have CH3, CH, right? CH3, where this one is net radical, and the other case here, this one is positive, like CH3. So this is another case again. So we also can have another situation whereby this one is broken here. We have this to be D, and then we have it to be CH3, CH, right? CH3, and then CH2, right? So we can have this to be plus here, and the other part here, CH3, CH3. This one is radical. Or we can have this to be CH3, CH, CH3, CH2, and this one is radical, and the other point, this one is the cation, right? So we can have different cases like this. So, but it's important to note that this is 1 degree carbon, right? Primary carbon. So this one is attached to this and this. So this one is tertiary carbon. This one is 1 degree carbon. This one is 2 degree carbon. It's attached to 2 carbons, right? This one is 1, 2, 3. It's 3 degree carbon. This one is 1 degree carbon. It's attached to just 1 carbon. This one is 1 degree carbon. So fragmentation would most likely occur with here or here, because they have higher degree, and this is due to the stability of the carbocation. Tertiary carbocations are more stable than other carbocations, that is 3 is greater than 2 degrees, greater than 1 degree. So if you fragment here, we're going to have this B and C, right? And if you fragment A, we're going to have this and this. So basically you can decide these two are basically the same thing. We are basically the same thing, right? So there's no point doing this actually, because these two are basically the same thing. So if you fragment between 3 and 2, there's going to be higher stability. So because this is 3, right, this one is going to carry the positive and this other side negative, like in terms of the more intense peak. This one is a primary carbocation, and this one is just and this one is 2 degree carbocation, and this one is 1 degree carbocation. So that's why we are selecting this to take the positive. So if you now look at the peak again, so let's look at this. This one is CH3, 15, and 13. That's basically 43, right? So it's losing 57, right? It's losing 57. So that's what we have here. 43 here is the most intense peak. Although this is the most intense peak basically, but this is the 43 that we obtained here. This is the 43 that we obtained here. So this 43 here is basically M plus minus CH2, CH3, right? So note that the base peak, this is the base peak, does not necessarily correspond to the molecular ion peak. This is the molecular ion peak. Although the molecular ion can also have the highest peak sometimes, but we cannot always say that because this is the molecular ion, it should have the highest peak. Don't mistake the two together. Base peak is different from molecular ion peak, right? So base peak is just the strongest peak, the ion with the highest abundance. It is usually assigned a value of 100%, and the intensity of all other peaks are reported as a percentage of the base peak, right? So now let's see this important aspect. So isotopic peaks. So isotopes have different masses. Mass spectrum can easily highlight the peaks associated with multiple abundant isotopes. So because different isotopes, let's say carbon 12, carbon 13, because they have different masses, right? So mass spec can identify the two of them. So right, so recall that we said that molecular ion peak gives the molecular mass of the sample molecule, and it is always the farthest to the left of the spectrum. So earlier on we said that the molecular ion peak is always the farthest to the left, right? So it is important that this statement is only true for monoisotopic substances. So well, I will explain this better. So what we just need to do now is this. Let's look at this chart. So substances containing different isotopes. So these are the major focus actually. These are the major focus here. So it is important to note that we have M plus, this is the molecular ion peak. So what we're trying to explain is this. Before we got to this point, we have always been examining substances that are just monoisotopic. So we only have M plus here. But substances that are isotopic, substances that have different isotopes, we can have M plus M radical ion. We can also have M plus 1, M plus 2 that corresponds to the different isotopes. So that means that if you are going to have your molecular ion peak here, we are also going to have some other peaks that are joined to it that are very close to this molecular ion peak, and these different peaks correspond to the different isotopes. Recall that I said that the mass spectrum can detect the masses of different isotopes. So that's what we are having here. So they are attached to it. So it's like you saying oxygen, for example. Now oxygen has how many isotopes? That's 2 isotopes. So these are D, right? So if we are going to have our M radical cation here, we're also going to have another that corresponds to this. There's no one here, so we're also going to have M plus 2 right here. So also looking at sulfur here, so let's say this is the spectrum for sulfur, and let's say this is the M plus, right? So there's also another peak here, so we're going to detect that also, right? And there's also another peak here, so we're also going to detect that one also, right? So they have different abundances. So if you try to look at chlorine is M plus ratio, it's M plus 2, right? So the ratio is like 3:1. So it's very important that when you see a peak and you look at the peak, the M plus is 3 ratio of the M plus 2, like the abundance. No, this part is the relative abundance, abundance, right? So let's say this one is 30% and this one is like 10%. So you can easily tell that this is corresponding to chlorine, and there's no M plus there. So also bromine, looking at bromine is like 50, is almost like 50-50. So let's say you have a peak like this and you have the M plus, and you also have the M plus 2, almost the same as the M plus. So this is like bromine rather. So a typical compound with no sulfur, chlorine or bromine has small M plus 1 peak and even smaller M plus 2 peak. So that was what I was saying here, that for substances that are not isotopic in nature, you may see smaller peak here, but they are not depicting anything at all. So but for if a compound contains sulfur, if a compound, okay, let's look at this. If a compound contains sulfur, the M plus 2 peak is larger than the M plus 1. So these are the things you need to note. So this compound contains sulfur, right? So the M plus 2, we said is like the ratio of these ones is like 4% of this major one, right? So the M plus 2 is larger than usual. So normally, if it's not isotopic, basically this M plus 1 is always a little bigger than the M plus 2. But the moment you see that the M plus 2 is larger than usual than the M plus 1, it's most likely telling you that the compound contains sulfur, right? So let's continue. So if chlorine is present, the M plus 2 is about a third as large as the M plus peak. So looking here, so if this one, let's say this one is I'm just saying, if this one is 30%, this one should be one should be like 10%, because the ratio of M plus and M plus 2 has to be 3:1, the abundance, right? So that's what we have here. So let's continue. So if bromine is present, the molecular ion and the M plus 2 ion have about equal abundances. So the molecular ion appears as doublets separated by 2 mass units. So basically, looking at this, we have M plus and M plus 2 similar, suggests when they are similar, it suggests that bromine is present, right? So when you see this one similar like this, it's most likely telling you that bromine is present. So now let's look at for iodine also. So iodine is recognized by the presence of iodonium ion, right? I plus. So the Mz is 127, right? So looking at this structure, we have, when you see a point at 127, just this one is always constant. When you see a point at 127, it's telling you that iodine is present, right? And it's further identified when there is a large gap without a spectrum, without a peak rather. There's a large gap without peak. So this is telling you, but once you see 127, that iodine is present, right? So that is just that. So now it's important to be able to recognize these recognizable elements in the mass spectrum. So we have bromine, the M plus 2 is as large as the M plus, right? So the chlorine, the M plus 2 is a third as large as the M plus, right? So for iodine, right, we know there's a large gap and there's I positive at 107. So nitrogen, so there's a nitrogen rule actually. So for a neutral molecule that is bombarded with high energy electron, right? So if the mz value is odd, there's most likely an odd number of nitrogen in the compound. But I don't think we need it for now. For now, we do not need that explanation. So here is just a practice for you. So you may want to practice with this. So point out which of the spectra below indicates the presence of sulfur. So looking at these two, they are almost the same. So this can tell you that there's bromine here, because these two are almost the same, and you are seeing 156. Yeah, these two are almost the same actually. These two peaks here. So let's look at the second one also. So here we have iodine here 127, and there's a large gap here as well. So iodine is present here, bromine here. So let's look at this also. So looking at this, you need to like measure the abundance. This one could be like 30, and this one could be like 10, and there's M plus, the M plus 1 there. So this is M plus, and this is M plus 2. So the ratio is like 3:1. So chlorine is present here, right? So let's see the last one. So I give you this last one to practice. So send your answer to the comment section. Yeah, drop your answer to the comment section. So in the next video we'll be talking about the fragmentation patterns, right? So this is the content of the next video. We'll be talking about fragmentation patterns, right?